Hello, in this video I'm going to take a first close look at radioactivity. I'm going to split the radioactivity videos into two. So in this one it will be more of a descriptive sort of background and what's going on video. And then the next one we'll be looking at the calculations, because there's the same old calculations that we keep on doing with radioactivity all the time, looking at how things are decaying essentially. So I'll put that in a separate video. So in this one, yeah, I mean, in terms of the background to radioactivity, I mean, it was discovered by accident in the 1890s by Henri Becquerel, and he came across this. He noticed that his supply of uranium was glowing during the night, which would worry people more nowadays than it maybe did with him back then. He also burnt himself on some radium that he was carrying around in his shirt pocket. So although that was useful from the point of view that it was the first step on the path towards radiotherapy for treating cancer, didn't do him a lot of good. He had the unit of radioactivity, the Becquerel named after him. That's the activity, the decays per second of radioactivity. But he was never going to be in for a long life, sadly, because he didn't really know, as no one did back then, what they were dealing with. So, I mean, perhaps fortunately for him, he died of a heart attack rather than radiation poisoning or anything like that. But I doubt the radiation helped very much. He was only 55 when he died, but he had quite the impact on the area of radioactivity, this new area of science. And you had a similar thing, obviously, famously with the Curies as well, who were also investigating this ionizing radiation a lot. You had the Becquerel, the Curies, Rutherford as well, who we've mentioned previously in this section. We're all investigating this ionizing radiation, i.e. this radiation that can detach electrons from other atoms, maybe breaking chemical bonds, creating new bonds, creating highly reactive free radicals that can do a lot of damage. So this is why radioactivity is potentially so dangerous, because it can mess with the structure of things. It can mess with the structure of your cells. So yeah, it's a potentially a dangerous thing. Although, as I say, we've harnessed it for things like radiotherapy, so it does have its uses. But yeah, we're certainly far from the days where people were painting radioactive paint onto their clock faces and then wondering why the Geiger counters were going nuts. So yeah, we've got a better understanding of the risks nowadays. So how do you detect radioactivity, and the behavior of these things? Is one thing to detect that there is a radioactive source with something like a Geiger counter, but how do you investigate the behavior? Well, cloud chambers are particularly good. So with cloud chambers you get air which is saturated with water. So essentially it is a cloud you're creating. So you're keeping it at relatively low temperature. Low temperature, low pressure, saturated air. And then as the radiation passes through the air, it ionizes the air, and water, because of its chemical properties, the way it's got this sort of polar behavior because of the arrangement of the H2O inside the molecule, the water will then condense on the ionized air, and that leaves a trail of water droplets along the radiation path. So you can actually see the path of the radiation going through the cloud chamber. So yeah, that's one way that you can look at it. You can also investigate the behavior of different types of radiation by applying magnetic fields, because the type of radiation that we've got is our alpha radiation. So this is essentially a helium nucleus. You've got 2 protons, 2 neutrons. So this is positively charged. It's got this +2e charge on it. You've got beta radiation, which is either an electron or a positron. So we've got a plus or minus E charge on that. And then we've got gamma radiation, which is photons. So we haven't actually got matter there, we've got energy. And these are less than 10 to the -13 meters as wavelengths. Now, you can see these are all different in terms of mass and charge. So when we apply these a magnetic field to these, they're going to behave differently. You know, if we set up some kind, pair of charged plates, make one of them positive, one of them negative, well, the photon's just going to go straight through. The electron, if we got beta minus decay, is going to bend towards the positive plate. If we've got alpha decay, it's going to bend towards the negative plate. And if we've got beta plus decay, it's going to bend even more because it's lower mass. So, or the charge to mass ratio is different to the alpha particle. So although we got half the charge, we got a lot less than half the mass. So we've got different behaviors going on there, and then you can have detectors sat in various places and see, what turns up where. So we've got that. Or you can do the old absorption test. So alpha particles, they get absorbed in sort of 2 to 3 centimeters of air. They're so big and cumbersome that they just start hitting stuff and get absorbed. Or you can put a sheet of paper in the way. So we've got that with an alpha particle. With beta particles, you've got maybe a meter of air, or say 2 millimeters of aluminium, something like that. For our gamma rays, well, these photons are very high energy. You need sort of 3 to 4 centimeters of lead in order to stop these. So again, you can do an absorption test on these as well to see how they're moving. So we've got various options to try and detect one thing from another. One thing that I should say about all of these forms of radiation, because it can confuse people, particularly when it comes to the beta decay, is all of it comes from the nucleus. So we haven't, if we got beta minus decay, this is not an electron that's coming from the shells of electrons around the nucleus. It's not some form of ionization. That is not what's going on. This is an electron which is actually coming from the nucleus. So you might be thinking, well, there aren't any electrons in the nucleus, so where do they come from? And well, yes, I mean, that's a good point. This is where the weak interaction comes into play. So all of this radioactivity is an interplay between the strong and weak interactions. But the weak interaction allows quarks to change flavor. So, and if you remember, so by flavor, I mean the up, down, charm, strange, top, bottom, these sort of things. So in terms of our standard baryonic matter that we're dealing with, which is all these up and down quarks, it allows them to change between each other. So if we've got beta minus decay, then we've got a neutron, which is an up and 2 down quarks, goes to a proton, which is 2 ups and a down, plus an electron plus an anti-electron neutrino. So this is what's going on. But if you look at the quark setup, we've had a down quark has changed into an up quark. We got the reverse thing happening in beta plus decay, where we've then got a proton, which is up, up, down, goes to a neutron, up, down, down, with a positron and an electron neutrino. So here we've got an up quark, changes into a down quark. So this is what's described by the weak interaction. So the forms of quantum mechanics and particle physics and such like, these really advanced descriptions that have been developed on those with the weak interaction, because the weak interaction has been unified into the electro-weak interaction. So the electromagnetic and weak interactions have been unified to a large degree, and it's descriptions inside that which will then describe how this change takes place between these the flavors of these quarks. So that's how we're getting these electrons and positrons coming out of the nucleus. So you want to make sure that you're clear about that's where it's all coming from the nucleus. Right, the last thing I'm going to say in this video is about the stability of different atomic nuclei. So you'll quite often see little graphs. I'm going to squeeze it on here. Doesn't need to be that detailed, where you've got neutrons, number of neutrons on the y-axis, and you've got number of protons on the x-axis. And the atomic nuclei that have been found to exist, they tend to lean. So if you've drawn a sort of y equals x in, it's in the same number of protons and neutrons. Elements tend to have more neutrons than protons. I mean, even at a basic level of understanding, you can see why that might be. I mean, the protons are repelling each other. The neutrons aren't being repelled according to the electromagnetic interaction. So, you know, you're going to get more bang for your buck from the strong force if you're getting more neutrons coming in than protons. But then, as we were saying about how these things arrange themselves into certain more stable energy levels inside the nucleus, you don't just want to pile up a whole load of neutrons. That isn't going to work either. You need to have both of them in order to get into this low energy state. So you get this sort of band that can exist of all known atomic nuclei. And inside this band, in the middle, this sort of little green section, sort of fuzzy section that you'll get in here, this area, these are all the stable nuclei. So there's this little area of nuclei that are stable. Anything which is outside of this, i.e. on this side you've got too many neutrons and on this side you've got too many protons. So you're still inside the bounds of these blue lines. So, you know, you're in here and you're in here. These will be the radioactive ones. I mean, outside of these blue lines, you just don't get any kind of, you don't get atoms with that ratio, that's a particular number of neutrons and protons. It has to be between these two blue lines, but the ones outside the green area are going to be the radioactive ones. So if you've got ones which have got, say, too many protons, then you're going to get, if you've got too many protons, then that's going to go to beta plus decay to get rid of protons. If you've got too many neutrons, then you're going to get beta minus decay in order to get fewer neutrons and more protons. So beta plus means that protons goes down, neutrons go up. That's what we saw here. Beta minus means that neutrons go down and protons go up, which is what we saw here. So that depends on which side of this green area that you're on. If you're just generally too big, if an atomic nucleus is too big and unstable, it's become a bit unwieldy, you've got a chunk that can just be dumped out in order to quickly get to a more stable state, then you're going to get this alpha decay in these bigger nuclei where you can just jettison a big chunk of stuff. Quite often these things aren't going to be isolated as well, although actually let's quickly mention if there's too much energy, then you're going to get the gamma decay, as in you've got a potentially stable or could be more stable setup of neutrons and protons. They just need to dump a bit of energy, then a photon can get booted out. But these will come in sets. You've got various shuffling around of these energy levels of neutrons and protons. They're rearranging themselves in various ways inside the nucleus, and that's chucking out energy, or maybe it's chucking out matter and energy is being thrown out here. And yeah, they come in groups. So you might get there's a beta plus decay, and then it chucks out a photon, you get that gamma decay, and then you'll have another beta plus or whatever. You might get an alpha decay and then a beta minus decay, these sort of things. It's not just a case of, oh yeah, you've got some nucleus, it does one radioactive decay and now it's stable. It might be that it goes from there, it goes to the next one, that then sits around for a bit and then decays to something else and then something else and onwards. So you can get these great big radioactive chains going on of one thing to another. So yeah, I would say the key part of all of this, I mean, understanding the basics points of the three different types of radioactive decay, but people tend to cover that pretty early in their science career and remember it fairly well. Certainly remember this about it's all coming from the nucleus, and then get a nice grasp on what's happening with this graph here of the relative numbers of neutrons and protons and what that means for an atom moving towards greater stability. And always think of this greater stability as being this rearrangement of what's in the nucleus of an atom in order to increase binding energy. This is what we're always seeking here, is this increase in binding energy, making things more stable. So yeah, just piecing all that together, you can really see the overlap here with what we've already spoken about in all of the nuclear physics. This is just a spontaneous way of behaving, as a spontaneous set of nuclear events that go on.